So in this example, we're told we have a closed rigid tank containing refrigerant R134A initially at 100 degrees C. Let's go ahead and sketch that out. So here's our closed rigid tank containing the R134A. The R134A is going to be my system. So I'll just draw a little dashed line around it. And the refrigerant is cooled until it becomes a saturated vapor at 20 degrees C. So there's going to be some heat transfer. I'll just draw it as Q into here. But since it's being cooled, we expect the energy to be leaving. So I expect my Q to be negative. And we're also told that the final state is a saturated vapor at 20 degrees C. That's pretty useful because that's two pieces of information. We know it's saturated vapor phase and the temperature at which it's a saturated vapor. So that's useful information for us to nail down the second state. We're told to neglect kinetic and potential energy effects during this process, and then we want to find the initial and final absolute pressures and the heat transfer. So to find the initial and final pressures, what I'm going to do is make use of this state information, that it's a saturated vapor at 20 degrees C, that the temperature here is 100 degrees C. I'll need another piece of information to nail down the other properties at that initial state. Since I'm only given one piece of information, you need two pieces of information to figure out what the state is. I have the two pieces of information for state 2 because I know it's a saturated vapor. That's one piece of information, and I know the temperature, so that's the second piece of information. But at the initial state, I don't have that second piece of information just yet. But anyway, that's what I'll need to do to find the pressures at the initial and final conditions. As far as the heat transfer, I'm going to make use of the first law of thermodynamics to find that, because that involves heat transfer. So I can use the first law to find that quantity. So let's first focus on the final pressure. And I'm just going to make use of the saturated vapor 20 degrees C information. So at state 2, I know I'm in a saturated, let's spell it properly first. I know I'm dealing with a saturated vapor, and I know that T2 is equal to 20 degrees C. So what I'm going to do is go to the saturated liquid vapor mixture table for R134A, since that's the material I'm dealing with, and I'll look at the table organized based on temperature, since I'm given the temperature here. So let's do that. So we have to find the right table first. Okay, so here we are. We're dealing with the saturated liquid vapor mixture. Excuse me, saturated liquid vapor mixture table for R134A, organized based on temperature. We said that we're dealing with 20 degrees C at state 2, and since it's a saturated vapor, it means all the properties are going to be given by this part of the table. So, for example, I know the specific volume is given right here, and the specific internal energy is given right there. And the pressure is the saturation pressure, which is right there. So those are my properties at state 2. So we just have to remember those numbers. And I've got them written down elsewhere, so I don't have to remember them since I have them written down. But let's go back and write them here. And so we can use that information with the saturated liquid vapor mixture table to find that P2 is 5.7171 bar. It's an absolute pressure. We know the specific volume at 2 is 0.035997 cubic meters per kilogram. That's just equal to the saturated vapor value at 20 degrees C. And the specific internal energy from the table was 241.02 kilojoules per kilogram. And again, that one's equal to the specific internal energy corresponding to the saturated vapor at 20 degrees C, because we know it's in a saturated vapor state. The reason I'm writing this information down is because, at least for the specific internal energy, I'm using that because I know I'm going to use the second law to find the heat transfer. And so the second law involves internal energy. So I'm making use, I'm writing this down because I'm going to ultimately use it. The reason I'm writing the specific volume is because this is how I'm going to connect information between the initial and final states. So remember, for the initial state, we're just told that we're dealing with 100 degrees C temperature, but I need another piece of information to nail down what the state is there, what all the properties are. And that additional piece of information is going to be the specific volume. And the reason I say that is because I know I'm dealing with excuse me, a closed rigid tank. So I know that since it's closed, the mass is going to be a constant. And since it's rigid, I know the volume is a constant. So since it's closed, I know the mass is a constant. Since it's a rigid tank, I know the volume is a constant. So the specific volume, which is just the volume divided by the mass, will also be a constant, right? So that means the specific volume at 1 is going to be the same as the specific volume at 2, which we already know. So I now know the specific volume at 1. I also know the temperature at 1. So those are the two pieces of information for me to find all the other properties. So with this information, now let me go back to the saturated liquid vapor mixture table, organized based on temperature, and just see where I am. So we have to remember these numbers. Okay, so let's go back to that table. Here we are, and we're dealing with 100 degrees C now. So we're down here, and here's the specific volume for the saturated liquid state. Here's the specific volume for the saturated vapor state. And our specific volume for state 1, we said, was 0.035997 cubic meters per kilogram. And when I look at that, clearly this is bigger than the saturated liquid state value for specific volume. And it's even bigger than the saturated vapor value. So the specific volume does not fall between these two. So it's not, state 1 is not a saturated liquid vapor mixture phase because the specific volume is bigger than the value for the saturated vapor. So it means it's expanded, it's bigger. You know, the R134A occupies a bigger volume, which means it must be in a superheated vapor phase. Excuse me. So let's go to the superheated vapor tables for R134A. So that's given right here. And remember, we're dealing with 100 degrees C, so we're going to want to look at the values for 100 degrees C in here. These again are this is the superheated vapor table for 134A. And just as a reminder, our specific volume is 0.035997 cubic meters per kilogram, and our temperature is 100 degrees C. So what I want to do, and my goal is to find the pressure and specific internal energy. So what I'm going to do is just look at the values corresponding to 100 degrees and look at the specific volume value. So here it's 0.21450 at this pressure of 1.4 bar. That specific volume is much bigger than what I have. So that means I'm going to have to look at a higher pressure because the higher pressure will squeeze the material and give it a smaller volume or smaller specific volume. So let me go down and just keep looking until I see a value that's pretty close to the 0.035. I'm going to scroll this down until I get pretty close to what I think is a reasonable value. Okay, so now we're pretty darn close. So if I look, put this here. So if I look here, 100 degrees, let me box them in. So 100 degrees temperature, and I look at the 7 bar, that specific volume is 0.040642. That's a little bit bigger than my value. Then let me go down to the value at 8 bar, and that value is right here, 0.035193. So my specific volume is somewhere between these two values. Okay, so to find out exactly what pressure it's at, I'm going to have to do a linear interpolation between these two values to find what the right pressure is. So the pressure at 1, if I do the linear interpolation, will look like the following. It'll be starting at 7 bar plus how the pressure changes, so 7 bar minus 8 bar divided by how the specific volume changes. So this would be the specific volume at 7 bar minus the specific volume at 8 bar times specific volume at 1 minus the specific volume at 7 bar. I think I've got that correct. Let me just double check. I'm sorry, I messed that up. This should be at 8 bar. Let me clean it up here. I should be starting at the smaller value of the two, so sorry for that. So that's my linear interpolation to find what the initial pressure is. So I'm taking the specific volume that I have, this specific volume right here, subtracting out the lower value of the specific volumes, which would be the specific volume at 8 bar. And then this is the slope of how the pressure changes over how the specific volume changes. And then this is the pressure I started with, which was down here, the 8 bar value, right there. So you can do the calculation and you'll get that the initial pressure comes out to be 7.85 bar. And again, that's an absolute pressure. So that's my initial pressure. Now, I also want to find what the initial specific internal energy is, so I'll have to do the same kind of linear interpolation, but now I'll be interpolating based on the specific internal energy, those values that I just boxed in. So that looks much the same. So I'm going to do specific internal energy at 1 is the specific internal energy at 8 bar plus how that specific internal energy changes. That's the specific internal energy at 7 bar minus the specific internal energy at 8 bar divided by the specific volume at 7 bar minus the specific volume at 8 bar times specific volume at 1 minus the specific volume at 8 bar. So it's just the same kind of linear interpolation as what I did here, but now I'm just using linear interpolation to find the specific internal volume at 1. And when you do the calculations, that comes out to be 309.268 kilojoules per kilogram. Okay, so let's remember those numbers. We'll write them back onto the original problem page. So just before I get off this page, I wanted to recap the approach we took. Is we know our temperature and specific volume at state 1, and what we did first was went to the saturated liquid vapor mixture table and discovered that this specific volume was greater than the specific volume for the saturated vapor, which means that we must be in a superheated vapor state. So we came to the superheated vapor tables for R134A, and then I went through the tables looking at 100-degree temperature values and compared them to my specific volume, and I found that this specific volume at 100 degrees was between the specific volumes at 7 bar and 8 bar. So I then did a linear interpolation between those two values, that's given right here, to find what the actual pressure is, and while I was at it, I also found what the specific internal energy was. Okay, so let's go back to the original problem statement. And let's just write down what we discovered. We found that we were dealing with superheated vapor, and through some linear interpolation, P1 came out to be 7.85 bar. Again, absolute pressure. These two pressures were one of the things we were asked to find. So let's box those in. And then we also found that the specific internal energy came out to be 309.268 kilojoules per kilogram. We're going to make use of that information in just a bit. Okay, so going back to the problem statement, we found the initial and final absolute pressures. And now we're asked to find the heat transfer. So to find the heat transfer, I'm going to apply the first law to that system. So let's write it out. And we're trying to find the heat transfer into the system. So that's what we're looking for. Now the work done by the system here is going to be 0. And the reason I know that is because we're dealing with a rigid tank. It's a closed rigid tank. So since it's rigid, there's no volume change, so there's no PDV work. There are no rotating shafts. There's no electricity, no springs. So there's no other work either. So this is just going to be 0. Now the change in the total energy of the system, that'll be the change equal to the internal energy plus the change in the kinetic energy, plus the change in the potential energy of the system. We were told to neglect changes in kinetic energy and potential energy. You know, the box isn't moving around, so its velocity is not changing. It's not moving up or down, so its elevation isn't changing. So these being zero are both very good assumptions. Now, we're asked to find what the heat transfer is, so just rearranging this, we're going to get the following. Q into is going to equal the change in the internal energy, which would just be U2 minus U1, right? So now we have to find what the U2 minus U1 is. Now if you go back up here, when it says to find the heat transfer, one thing I just want to highlight is that actually it's saying the heat transfer in kilojoules per kilogram. So it's actually per unit mass. It probably should have said heat transfer per unit mass in kilojoules per kilogram. So let's fix that. I just know this based on the units. I just noticed it. Heat transfer per unit mass is what it should have said. And the reason I'm basing that is just based on the units, kilojoules per kilogram. So what I'm really trying to find here is the Q into per unit mass. That will be equal to the little u at state 2 minus the little u at 1. It's just taking the internal energy and turning it into the specific internal energy because I'm dividing through by the mass. Just remember that internal energy is mass times specific internal energy. Okay. Well, we've already calculated these values, right? The U2 value is given right up here, and the U1 value is given right here. So we actually have those values, so we can plug those in. We would find that the heat transfer into the system per unit mass would be minus 68.2 kilojoules per kilogram. And since it's negative, what it means is that the heat, instead of going into the system, it's actually coming out. And that is consistent with the fact that it says it's being cooled. So we're removing energy from that system. So anyway, it's fine that we have the negative here. Since we originally showed it was going in, it just means it's actually, in fact, coming out. Okay, so just to quickly recap this problem, what we did is the initial part of the problem, we just made use of the information we're given, specifically the saturated vapor at 20 degrees C, to find the final state, because we need two pieces of information to determine all the other properties. To find the properties at 1, we recognize that the specific volume remained constant during the process, so that information coupled with the given temperature, we could determine these properties at the initial state. We had to do some linear interpolation to do that. And then to find the heat transfer per unit mass, we made use of the first law, recognized that there was no work being done because it was a rigid tank, and then just used our specific internal energy values to calculate the heat transfer per unit mass. And we found that the heat transfer was actually coming out of the control volume. Okay, we'll end it there.